Hi everyone, my name is Renjie Zhao, a PhD student of UC San Diego. Today I'm going to introduce our work on NFC Plus, breaking NFC networking limits. This work has been done during my internship at Alibaba Group. Today's major internet companies are transforming traditional e-commerce into a new model that is called online to offline commerce. Over the past few years, we have witnessed the great success of many companies following this transformation all over the world. And we know that the booming of O2O is just about to start. Let's take a look at the chart shown above. We can see that today's online sale is just 10 to 20% of the whole online and offline combined together. So there is a $1 trillion opportunity, and the O2O trend will continue to grow rapidly to close this gap. More importantly, this year, the COVID-19 pandemic may completely change the lifestyle of people on Earth. Now, many people like me totally rely on O2O grocery and food delivery for living. We expect these changes will further accelerate the growth of the online to offline services offered by major internet companies. As one of the largest O2O companies in the world, Alibaba Group owns many subsidiaries such as Cainiao, Hema, and Ele.me, which covers O2O services from not only in logistics, but also in new retails such as food and grocery delivery. Based on the operating experience, we found that the core problem people face in the ever-growing O2O services is how to do efficient object identification at large scale. Now, let me explain to you why we need object identification. Take Cainiao logistics network as an example. The product purchased online have to be delivered as soon as possible through a logistics network to arrive at customers' hands. In this scenario, you need to identify the package in almost every logistics operation in order to route it to the destination. Today, you can usually see a label like this attached to a package delivered to you, which is for this purpose. The flow of logistics network today is becoming extremely large. For example, the total delivered package number of Cainiao Smart Logistics Network is 30 billion in 2019 and is expected to be 150 billion in 2025. To meet the demanding scale and efficiency challenges, we can no longer rely on traditional barcode and QR code, which becomes slow, labor-intensive, and error-prone. To solve this problem, UHF RFID has been widely acclaimed to be the vital enabler for object identification. But what we see is that although UHF RFID has been there for 30 years and after numerous trials in real-world deployments, it only finds its use in very specific application scenarios such as apparel retailers. What is the problem? After talking with the vendors and logistics service provider, we found that the main issue of UHF RFID is on the reading accuracy and tag cost. Today, we will focus on the accuracy. Taking a logistics example, a worker is using trolley to bring 20 labeled packages out of a warehouse. The trolley will first pass a checking zone to make sure whether the correct ones are leaving. By using RFID, worker will not need to scan the labels manually. The reader in the checking zone can do the detection fast and automatically. There can be 3 kinds of reading result. First one is all of the correct tags are detected, which is great, but the life isn't always perfect. Sometimes there will be 19 tags read, which means misreading happens, and sometimes there will be 21 tags, which means cross-reading happens. The package outside checking zone has been detected. Both results may lead package lost or introduce significant verification cost. This barriers the real RFID deployment. So let's look into the reason why this happens. First, the main reason of misreading is that UHF signal is influenced a lot by objects. When the object is between reader and tag, the signal strength will be attenuated a lot by the object. The liquids like water, drinks, the metal in the package, nearly everything in our daily life will cause attenuation to the RF signal and cause misreading. Then, what is the reason of cross-reading? As shown here, wireless signal will be reflected by indoor environment. The signal reflected might be combined constructively at some locations. As shown in this plot, the signal strength can be pretty large at a long range and results in reading text which is far away from the tracking zone. Because of these reasons of misreading and cross-reading, we see that the accuracy of UHF RFID is only around 90%. We have talked with vendors, logistics service providers, and the manufacturers. What they expected is an accuracy of higher than 99.9%. The 9.9% difference may lead to billions of dollars lost for handling misdelivered packages. Many vendors even discard the RFID setup after deployment because they do not see any benefit with the low accuracy. Therefore, one thing we want to emphasize here is that in the real-world deployment, the median error or even 90% error make no sense. The tail error is the most important issue and hard to reduce. By analyzing the reasons, we found that the main issue is on the physical properties of the signal. Any algorithm-based technique will not solve the basic issue introduced by the physical properties, because it is mainly determined by the frequency. Therefore, we choose to change the mind from struggling with the UHF RFID electromagnetic wave to find some other replacements. What we found is that the NFC at 13.56 MHz with magnetic wave has much better properties. Unlike UHF signal, the impact of material to magnetic signal is very small. By fixing the location of reader and tag, we can measure the impact by calculating the signal difference when the object is there or not. We picked a bottle of water, can Coke, and box of milk as an example. The object influence to NFC signal is much smaller than to UHF signal. For the carrier frequency of 13.56 MHz, the wavelength is about 22 meters. This means that the working zone will be located in the near field region. The waveform will be pure magnetic, which means there will be no multipass effect, and the strength drop will be much faster compared to UHF RFID far-field signal. The NFC reading will be perfectly limited to a range and will not meet the cross-reading issue. Because of these properties, it seems that NFC is a perfect solution compared to UHF RFID. However, it also has its own issues, which is the reason why it is not adopted, even it has longer history than UHF RFID. The issues of NFC is on range and orientation. Because the magnetic field attenuates much faster, the typical reading range of NFC is really short. For example, the commonly used portable NFC module only covers several centimeters. Even the longest NFC today will only cover 90 centimeters. Then, since the magnetic field is closed-loop field, the orientation of tag will influence the strength a lot. For example, when the tag is perpendicular to the field, the tag signal is the maximum. If the tag is parallel to the field, the tag cannot be read. Because of these two issues, the NFC technique is mainly limited to proximity applications. Our NFC Plus system solves these two issues. It can boost the range up to 3 meters, and the tags can be random orientation. And the final accuracy can reach the 99.9% requirement. To understand how we deal with the issues, we need to first introduce the architecture of an NFC system. An NFC system consists of a reader with a TX coil acting as antenna. The tag will also have a coil with a tag chip. They are designed following the principles of inductive magnetic coupling. As shown here, the reader will generate a magnetic field which is passing through the tag's coil. the tag and reader will couple with each other. Therefore, from the traditional view, the coil of reader and tag will form a loosely coupled transformer. This model can precisely show the behavior of the circuit's components, but it will also combine all the influence of range, coil parameters, and coil orientation into a coupling factor. This varies solving the range and orientation issues. Therefore, NFC or wireless power transfer usually requires moving the tag or RX to a proper location and orientation to maintain a large enough coupling factor K. Therefore, in our design, we are looking in a modern communication view so that we can implement the well-developed communication techniques to NFC. Because of the low coupling between reader and tag, we can neglect the tag influence to the reader, and then separately analyze the magnetic signal generated by the reader and received by the tag. More specifically, the analyzing procedure can follow 3 steps. The first step is to calculate the current on the reader coil. Then, using the calculated current to analyze the generating magnetic field. Finally, based on the magnetic field, the signal received by the tag can be calculated based on Faraday's law of induction. Following this analyzing procedure, we can decouple the influence of reader circuits, range, and tag orientation, and then solve the range and orientation issues independently. We will first introduce our first technique on solving range issue, which is doing a resonance engineering. Resonating happens at the first stage. By adding a shunt capacitor to the reader coil, the circuits will form an RLC resonator. The energy stored in the capacitor and the inductor will be transferred to each other, and the current on the coil IL will be Q times of that from power source. The Q here is called quality factor. After calculating the magnetic field strength in the second step, we can see that the signal strength is proportional to Q. Then a larger Q means a longer range. But too large Q will cause issue to Rx. As shown here, the reader will first generate signal at a carrier frequency of 13.56 MHz. Then the tag will do double sideband modulation with a small subcarrier. When the TX and RX are sharing the same reader coil resonating at 13.56 MHz, large Q will suppress the tag signal a lot and reduce the reading range. But in fact, the required bandwidth is mainly dominated by the subcarrier. For TX or RX communication, the bandwidth is smaller than 100 kHz. So there can be a large room for large Q if we separate the TX and RX coils. That is, let the TX coil resonate at 13.56 MHz and the RX coil resonate at 14.01 MHz. With this design, the Q value can be around 20 times comparing to the current accepted value, which boosts the range a lot. The second technique is using multiple coils to deal with the orientation issue. There has been some work on using multiple coils in wireless power transfer. Since the TX and RX are close coupled, the feedback can be measured and can do closed form calculation. Since the coupling of NFC at a long range is negligible, this feedback-based method is not applicable to NFC. Therefore, we need to accept the open-loop scanning method like the RF beamforming swapping. However, in this method, the swapping complexity exponentially increased based on the M phase number and the N transmitting antennas, which can be very large and introduce unacceptable time complexity. We found that under low coupling scenario, the optimal phase combination between multiple coils can be identified by binary searching 0 and pi phases. This can reduce complexity substantially. We have another two techniques which utilize the properties of low-frequency magnetic wave. One is the passive self-interference cancellation design. It contains the high Q coil rejection introduced by the TX-RX separation, the ultra-narrowband crystal notch filter, and the filtering at intermediate frequency and digital domain. This technique improves the reading range of RX. Another one is the passive magnetic repeater design. The magnetic repeater is excited by the TX coils and does not need other power source, such as batteries. This technique can further improve the reading range and the reliability. We have built a self-designed reader. The hardware design contains a multiple-chain TX module, TX2RX interference cancelled RX module, and an STM32 ARM processor. The coil of the reader is a 0.9 meter by 1.1 meter aluminum loop, and the tag we use is a commercial ISO 15693 NFC tag. For the software, we implemented the ISO 15693 compatible protocol in C++, which contains multiple access functions. The final reading rate is 50 tags per second. We'll first evaluate the range performance. The distance between the tag and NFC readers are changed to find the longest range of commercial readers. The smartphone can only read tags around 1 centimeter away. An open source NFC platform, Proxmark, can read tags at a distance of no more than 15 centimeters. As a result, they are mainly used as a tool for proximity applications. To our knowledge, RD5101 reaches the longest reading range of an NFC reader, which can read tags up to 19 centimeters away. In our NFC Plus setup, the TX coil and RX coil are placed 3 meters apart, and the tag moves in between. By utilizing all the techniques in NFC Plus, our system can cover the whole range of 3 meters. We then conduct a simple experiment to illustrate the effectiveness of NFC Plus's magnetic beamforming comparing to normal NFC and the UHF. The tag will be placed in front of reader and rotated by 180 degrees. The measured signal strength loss is shown here. You can see that both the UHF RFID tag and the NFC tag experience more than 30 dB signal strength loss when its antenna is perpendicular to the reader antenna. Well, in NFC Plus, another pair TX and RX coil are used and the magnetic beamforming is done. The result shows that even in the worst case, the NFC Plus only experiences around 3 dB signal strength degradation. Here, we will show a lab demo simulating the logistic network case. In the region, we deployed 2 TX coils and 2 RX coils covering a tracking zone. 16 NFC tags are attached to some most RF unfriendly merchandises, such as bottled water and Coke, canned Coke, and boxed milk. The merchandises are placed on a trolley with random orientation. The trolley is pushed through the tracking zone, and the UID of tags are red. By comparing with the ground truth, we can get the misreading number and the cross-reading number. We also did similar evaluations for NFC and UHF system. In the evaluation, we did over 10,000 times tag reads to evaluate the tail error performance. We observed that NFC Plus will miss only 0.03% of the tags passing through the tracking zone, much better than the commercial RD5101 NFC system, which misses 40%. When UHF tags are placed on purpose, that is, all tags have line of sight with the reader, the UHF RFID system missed 1.54% of the merchandises. When merchandises are placed with random orientation, the misreading rate of UHF RFID jumps to 23% due to its low reliability under the blockage. When doing the reading experiment, We also place plenty of tags randomly out of the tracking zone. From the result in the second figure, we can see that neither NFC Plus nor the commercial NFC read any tag outside. In contrast, UHF RFID experienced a 42% cross-reading rate. The poor cross-reading performance is an inevitable sacrifice when the UHF RFID is tasked to achieve a high reading rate for the tags in the tracking zone. In summary, NFC Plus is the only system that covers long range with arbitrary tag orientation while achieving over 99.9% accuracy. We also want to give two take-home messages. One is that the tail error is crucial in geo deployment. Researchers also need to keep an eye on this. The second is that we want to bring magnetic communication back to researchers' side because the physical properties of magnetic field is extremely superior in many large-scale applications.